We thank Dr. Ibrahimi for her great presentation. And now, ladies and gentlemen, it's my pleasure to introduce Dr. Abdous, a young and promising researcher whose groundbreaking work during his PhD at Sharif University has already made a significant impact on the field. Despite his youth, Dr. Abdous has demonstrated remarkable talent and dedication, producing novel and valuable research that has garnered widespread recognition. His innovative contribution promised to shape the future of his field and inspire future generations of researchers. Please join me in extending a warm welcome to Dr. Abdous as we celebrate his achievements and anticipate the bright future ahead. Dr. Abdous.
Hello everyone, I am Hatef Abdous, PhD and lecturer at Civil Engineering Department, Sharif University of Technology. It's my honor to share my findings and current research on curved RC shear walls. The outline includes at first taking a glance survey at the current technical literature, establishing a state-of-the-art experimental program to assess the cyclic response of curved RC shear wall, introducing a novel loading system apparatus capable of accommodating the in-plane and out-of-plane motion of the specimen, experimental findings and observation, a reconnaissance investigation on the damage evolution process and hysteresis performance of the tested curved RC shear wall, analytical formulation and parametric investigation, and conclusion. Non-rectangular RC shear wall can generally be cataloged as an I, T, U, L, E, and Z-shaped structures. This type of structure intrinsically suffers from the shear lag influence, and by adopting curved shape and eliminating the web flange intersection, the shear lag effect will not be a major concern. In design practice, curved structural elements are generally employed to fulfill some of the architectural and aesthetic requirements. However, due to the complexity existing in the construction, casting, and testing process of curved structural elements, the structural behavior of such salient elements remains essentially unknown. Taking a glance at the current technical literature indicates a wealth of experimental, analytical, and numerical investigation on the cyclic response of non-rectangular RC shear wall. However, a paucity of decent and in-depth investigation does obviously exist in the technical researcher to assess the cyclic performance and structural performance of RC shear wall. In this regard, an experimental testing program has been designed and constructed at Sharif University of Technology. A heavily instrumented curved RC shear wall with 1/3 scale has been designed, constructed, and pseudo-statically tested under the cyclic loading. The main assumptions made in the experimental study include no axial loading, no boundary element, and applying the lateral loading to the centroid of the cross-section. As shown in the plan view of a curved cross-section, an offset does exist between the shear center and centroid of the section. Hence, a torsional moment will be introduced in the section that should be considered in the loading apparatus system. In this regard, in order to accommodate the out-of-plane motion of the specimen, a new loading system apparatus has been designed. The main mechanism of the loading system includes two interconnected sway wells connected through special connectors. The main mechanism has been rested on SC-reinforced elastomeric bearing, which include on a block carriage with a special rolling system and a linear guideway to freely move in order to provide out-of-plane motion. The rolling circulation system is shown in this slide. The test unit includes three main sub-assemblies, including the block foundation, wall panel, and the loading head. The main mechanical properties are shown, the main geometrical properties of the tested wall is shown in this figure. The construction sequence of the test unit is provided in the following slide: a heavily reinforced block foundation, anchorage, and a special connector are considered to clamp down the specimen to the strong floor. The exact location of the longitudinal rebar are specified, and at the first place, piecewise S-drop due to the spatial cross-section of the section. Extension of the longitudinal and transfer reinforcement to the block foundation. Piecewise S-drop, cross size, and accurate leveling of the inner and outer piecewise S-drop. Framework of the wall panel. Pouring concrete and curing of the wall panel. Using a CNC machine to accurately specify the exact location of the wall section on the framework of the loading head. Employing 5 continuity plates in order to uniformly transfer the applied cyclic loading. And final stage of the construction. The mechanical properties of the material has been considered using the UTM test. As the thickness of the wall cross-section was essentially small, that is 10 centimeter, a self-compacting concrete with target strength of 45 megapascal has been employed, and the J-ring test of the self-compacting concrete is shown in this slide. 14 strain gauges has been affixed to the vertical reinforcement and aiding on their transfer reinforcement. A special protection plan using SP tape and VM tape has been employed in order to protect the embedded strain gauges, and no malfunction and failure was detected during the testing process. 10 strain gauge rosette with 3 sensing element has been affixed to the wall panel at both faces in order to detect the strain profile for both the wall panel. 9 LVDTs have been employed in order to capture the in-plane and out-of-plane motion of the test specimen. 7 high-resolution cameras has been employed in order to thoroughly capture all the details during the testing process. And the loading protocol has been applied during 8 phases. The loading rate was 5 mm per minute, 1 mm increment for target displacement with 2 identical cycles at each displacement target up to the maximum target drift of 2%. During the testing, 10 key stages were extracted from the cyclic response of the tested curved RC shear wall. The performance level of the tested wall is shown in this figure. At the first plate, at the initial stage of the loading, horizontal cracking due to the combined action of the bending moment and warping torsion has been developed and formed in the wall panel. By increasing the loading excursion, diagonal X-shaped cracking formed and developed all the wall panel at both the inner and outer faces. Yielding of the longitudinal rebar, concrete cover spalling, sliding at the interface of the foundation and the wall, concrete cover spalling and internal exposure of the longitudinal rebar, buckling of the longitudinal rebar and fracture of the longitudinal rebar at the outermost layer, and at last, failure of the specimen at the latest excursion of 2% drift. Cracking pattern and damage evolution process of the tested wall is shown for different drift values. The sequence of hysteresis response is shown in this slide, and the full hysteresis response indicate that the spindle-shaped hysteresis response with symmetric behavior. The bearing capacity degradation indicates the stable performance of the wall due to the bearing capacity. In order to assess the contribution of the longitudinal and transfer reinforcement, the strain profile has been derived. Almost all the longitudinal rebar has been yielded, especially at the base level of the wall, and a general decreasing effect was observed along the height of the wall. In order to assess the contribution of the inner and outer piecewise S-drop, the strain profile are provided and plotted. Due to the small thickness of the wall, no meaningful discrepancy was observed for the identical level of transfer reinforcement, and no evident sign of yielding was observed for the transfer reinforcement. In order to assess the torsional performance of the tested wall, the LVDT measurement and image processing data have been utilized, and the results indicate the significant out-of-plane response of the wall. In this slide, the torsional performance of the tested wall signifies the out-of-plane motion of the tested wall. Within the analytical formulation, we derive analytical formulation for the stress and strain development of non-rectangular and flange and curved RC shear walls. Equivalent non-rectangular flange sections are introduced based on the material efficiency criterion. All the geometrical properties used within the analytical formulation are derived for a general section for curved, T-shaped, L-shaped, and U-shaped RC shear wall. In order to compare the structural performance of the curved RC shear wall and those of equivalent section, 6 non-dimensional parameters introduced to assess the induced response of the curved flange RC shear wall with respect to the curved RC shear walls. The results are computed for 6 different RC shear walls with those equivalent cross sections. The results indicate the superior performance of the curved RC shear wall in comparison with its equivalent cross sections. Within the parametric investigation study, 90 curved RC shear wall has been simulated in the Abacus software for 3 categories of short, squat, and slender RC shear wall. An applicable formulation has been proposed based on the ACI approach for the shear strength estimation of the curved RC shear wall. The main parameters include 9 parameters that employed based on the sensitivity analysis. Based on the regression analysis, coefficient of alpha 1, alpha 2, and alpha 3 and R factor has been defined. In order to further verify the accuracy of the proposed analytical formulation, the result of the experiment based on the actual mechanical and geometrical properties has been considered in the proposed formulation. The results indicate that the proposed formulation can well predict the response of the shear capacity and response of the curved RC shear wall with less than 10% error. Conclusion. The structural performance of curved RC shear wall has been assessed within the experimental, analytical, and numerical investigation. The tested curved RC shear wall indicated a stable cyclic performance with no discernible strength and stiffness degradation. The induced warping torsion due to the eccentricity of the shear center and centroid of the section was largely responsible for the governing failure mode of the curved RC shear wall. And due to the failure mode, special care should be given to adopt a well-designed boundary element. The contribution of the longitudinal bar was more significant as compared to those of transfer reinforcement owing to the shear span ratio of the wall, that is 1.3. The proposed analytical formulation was capable to well predict the shear strength capacity of the wall. And findings of this research revealed that the curved RC shear wall can potentially be a well-deserved substitute instead of the conventional flange RC shear wall. Interested researchers can consult the research of or current research on curved and flange RC shear walls. Thank you so much.
Thank you for a nice presentation. We have a bit time. Do you have any question? Okay.
I would ask a question. If there is still a possibility, I'm wondering, on slide number 26, you showed the strain rate and the history of the loading. And I'm wondering if you would consider FEMA loading perhaps to keep the amplitude the same for a couple of cycles to let the system settle down. And maybe another good test for the system would be sweep testing, keeping the amplitude the same, increase the frequency, something like that.
In non-rectangular RC shear ball, the current research conducted in this field has been focused on capturing all details during the testing process. In this regard, the increment has been considered 1 millimeter per second in order to thoroughly capture all the details during the testing process. In this regard, this loading protocol has been considered for this testing. It's common for non-rectangular RC shear bar to consider this loading protocol in the simulation process.
Sure. In dynamical structure, when you apply a load to it, when you shock the structure would take time to respond. And if the frequency of the structure is different from that, let's say it's smaller than your shock, the structure needs time to respond. So when we keep the amplitude a couple of times at the same rate, we would give the structure a little bit time to see what happened. Of course, when you're analyzing the whole thing, you're pressing the structure a little bit too much. But that you still get the result. Thank you.
Thank you so much.